Okay, we're in week 2.5. I'm on page 188. Practice 5F problem number 3. This is video Physics25BBlake, and this problem is pretty challenging for high school level. So I'm going to show you 2 ways to do this problem. The first way is probably the way you would try to attack it if you had an idea what to do, because it's more intuitive for a student, I think. But then you get stuck on how to find the distance, because you either have to go back, chapters back to x equals x sub 0 plus v sub 0 delta t plus 1/2 a delta t squared, which you're going to forget about maybe, or you have to use a graph, which students never like to use to do. The third way is actually a little slicker and shorter, but it's less intuitive. So let's try this. Build your questioning a little bit. First of all, power is going to be equal to the work it takes to accelerate this car plus the work you have to do to overcome friction combined divided by time. Power is work over time, but this instance we have 2 kinds of work. One is to overcome friction as you push it, and the other is to speed the thing up, so the work goes in to make it go faster. I have some videos, by the way, I might assign it later this week for you to watch about power, force, time, velocity, kinetic energy. Now I copied over our work energy principle little diagram where kinetic energy is equal to potential energy is equal to work is equal to kinetic energy. So you can transfer one of these into the other. Now, because of this, since we're going to accelerate that car, the work it's going to accelerate this car is going to result in kinetic energy, which we can find. And then we can find this separately, the work separately. Kinetic energy is 1/2 mass times the ending terminal final velocity plus force times distance. So you're going to say, okay, I know how to find distance based on what you said a little bit ago. It's x final, we're just going to call it d this time, but it's the same thing. X sub 0 plus v sub 0 times delta t plus 1/2 acceleration times delta t squared. Put that in there. Well, if we're starting from rest, we don't have this guy and we don't have an initial velocity, so it's going to get a little bit easier. And we don't have A. Here's the problem with that. Here's why this gets complicated. We don't have A. So you've got 2 ways to get A. One, well, you got 2 ways to get D. The one that's actually easier is the one you're going to like least. Your velocity goes up as your car speeds up. It's going up at a constant rate, we're going to say. This problem is actually more complicated than we make it. Because that's not normally going to happen, and I got a video that talks about that. But your acceleration goes up at a constant rate. So all you need is to get the area under this triangle, and you've got the distance d, which can go here. Area is x, or displacement. We're going to call that d also. So that's 1/2 base times height. 1/2 the base is 12 seconds. The height is 18 meters per second. So you can put that straight in for D and you're done. That's not so bad. If you get to this point and you're stuck, distance is 1/2 AT squared, you could go A is V over T or delta V over delta T. One of your delta T's cancels, and it's 1/2 delta V times delta T. So it's half your maximum velocity of 18 times 12 seconds, which is the same answer. Both of these are 108. Now you probably would have got stuck here or here, or here. But it works. Once you have that, then you can plug in your equation. You've got the 1/2 mass is 1,500 kilograms, velocity max is 18 meters per second. You got to square that, plus 400 newtons of force for the 108 meters. Multiply all that together, add it, divide by 12, you come out to be 23,850 newtons. There's an easier way to do this. If we say that the power is equal to the kinetic energy divided by the time over the accelerating part, plus force times velocity for speed, and this is average velocity, then we can do this. You can't use the maximum velocity here because the velocity is increasing like so. And you're not going maximum velocity the whole time. So you actually want the average velocity, and the area under here and the area under here are the same. That would be something experience would tell you. So you can't just stick 18 in there. You got to add the average velocity to do that one. Kinetic energy is 1/2 mv squared over t, and force times average velocity. We'll go view power, which comes out to be kinetic energy divided by 12 and 400 newtons times 9 meters per second. And that comes out to be, this is 3,600 watts. This is 243,000 joules over 12 seconds. Joules per second is watts, and this, and you get the same answer, 23,850 watts. Number 4, a rain cloud contains 2,660,000 kilograms of water. How long would it take for a 2,000 watt pump, 2 kilowatts, to raise the water to the cloud's altitude of 2 kilometers? Well, it'd take a while. There's a lot of water up there. It's way up. So your pump is 2,000 watts, 2,000 joules per second. The work you need to do is the gravitational potential energy, mgh. Your force times distance is equal to m times g times h. Remember the triangle. Okay, so when you go m times g times h, you have to do 5.22 times 10 to the 11th joules. That's a ton. Well, it's more than a ton. It's a whole bunch of tons. So all we got to do is work our power equation. Now look how I did this. I didn't do it the same way. I could have went power is equal to work divided by time, and I could have put 5.22 times 10 to the 11th up here, and I could have put 2,000 over here and divided one, took t over here is 5.22 times 10 to the 11th divided by 2,000 joules per second. So I got joules divided by joules per second. It would have worked. That's fine. If you did that, that's perfect. For whatever reason, I just used my power as a unit conversion, 2,000 joules per second, and I ended up doing the same thing, dividing 5.22 times 10 to the 11th by 2,000 joules. Joules cancels, I end up with seconds, and it comes out to be 2.61 times 10 to the 8th seconds. Now, I don't have that converted to hours and minutes or whatever. I don't have the answer in front of me either. But that's how you do that, either way. Okay, let's continue. Section review, where you have a parachute jumper. The parachutist, skydiver, going to jump out of an airplane and he lands on the ground with a speed, by what amount was mechanical energy reduced due to air resistance? So basically, the jumper is way up in the air, gravitational potential. The parachute is going to do work on the way down, on the way down, and the person is going to end up with a kinetic energy. So we want really work. It says work. It doesn't. I have said work by the parachute. It says is what amount was the mechanical energy reduced? That's just work. So I have this number and this number. I'm going to take kinetic energy over here and look for the work. So we have those two. We have mgh, and we have 1/2 mv squared. Somehow I got distracted. And the work is equal to mgh, 50 kilograms times 9.81 meters per second squared times 1,000 meters. Subtract 1/2, 50 kilograms times 5 meters per second squared. This number's really big. This number, not so much. It doesn't, I mean, the fact that he or she hits the ground going at 5 meters per second is a very tiny amount of energy depending, compared to falling from 1,000 meters out of the sky. So you're taking 490,500 joules and subtracting only 625, which comes out to be 489,875 joules. Now we want the power. So or we want the average force, I guess, not the power. Work is average force times distance, so you just take 490,000 newtons more or less, divided by 1,000, and it comes out to be 490 newtons. Then you have a student climbing a rope. What's the power output and the work? Well, let's do the work first and then the power output. That makes more sense. So you've got a student who's got a mass and a gravity and a height. For whatever reason, I put m times g times d. That's okay. It's the same thing. It's just a vertical distance. Okay, so the student has a mass of 50 kilograms times 9.8 meters per second, 1 meters per second squared, times 5 meters vertically. The amount of work done is 2,453 joules, which is also the gain in gravitational potential energy. And we have to divide that by, 200 watts to find out how much time it took. 200 watts is quite a bit for a climber. So bring T up here, divide by 200, and you get 12.3 seconds. So that'd be pretty good. How are time, energy, and power related? I probably will have to add to my notes here because I was thinking about this on the way home yesterday. Okay. Power is the change in energy per unit of time. This could be work, this could be gravitational potential energy, this could be elastic potential energy, it could be some combination of the three. This should really be mechanical energy for this chapter, but it could be electrical energy, it could be thermal energy, it could be nuclear energy. That's all we need for that one. And by the way, I was thinking ahead. Looking ahead, there are some equations we can use. If we look at, we already said power was force times distance divided by time, but we also said power was equal to force times speed. Or force times velocity. That could be, I will leave the average off of there because if it was instantaneous, it'd be something else. If you are rotating something, we'll have a twisting force called torque through some amount of angle, which is analogous to distance divided by time will give us work. But we can also go torque times omega, which is rotational velocity. For electrical stuff, power is current times velocity. So this bottom part doesn't answer the question we're looking at here. Here's the answer to the question, but I want to point these out because we're going to talk about these later. There are more ways by this. You could talk about the rate you heat up a gallon of water, or how a power plant works, or a gasoline engine. So there's way more equations than these that talk about energy. Let's go on to the next one. Okay. You see what time we got. Let's put that on another video.